also a tonal language,
Oh, yeah,
which makes it even harder.
yes, especially for, yeah, that's right. So let me give you, actually, we're gonna move on to Galois theory today, which is one of the most exciting parts of the course. But let me give you a couple of, here's a couple of kind of applications of this. How many 5x5 nilpotent matrices are there up to similarity? So I'm not asking exactly how many there are because there's infinitely many. Well, unless you're over finding a field, maybe. But how many are there up to similarity? So here's a question for you. So let me recall for you. A matrix A is nilpotent. In A and 0. Anybody know anything about nilpotent matrices that might be useful if trying to figure out this problem?
All the eigenvalues are zero.
All the eigenvalues are 0. Note, if you have AX equals lambda X for some non-zero eigenvector X, then A squared X is lambda and let me say because if I don't make that assumption, then it would be a field day. And so in particular, A n X is lambda n X. But if the matrix is nilpotent and this is 0, therefore lambda n equals 0, so lambda equals 0 if you're over a field, right? And your vector is non-zero. Yes.
You can argue that also with the Jordan canonical form, right?
Right. That's right. Well, so now armed with this, I know no matter what your field is, the eigenvalue 0 is in it, right? So you can actually do the Jordan canonical form, right? So A has a well, A has some Jordan canonical form, and a Jordan block is a form 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1. That. And of course, in our particular situation, you can assume those matrices are sized 5 by 5 or less, right? So really, here's all you have to consider. What are your elementary divisors slash invariant factors, which of course in this case are the same thing, because basically what is true about the characteristic polynomial of a 5 by 5 nilpotent matrix? Characteristic polynomial might be x to the 5th, right? And so all of its elementary divisors and all of its invariant factors have to be the same because there's only one prime. There's x, and it's x to the 5th. So yes.
What happens if roots of the characteristic polynomial isn't in the field.
Then so if you have at least one root that's not in the field, then you can't do a Jordan canonical form over that field. You'd have to go to the minimal extension where you've got all those roots.
Yeah.
So that's a great limitation of the Jordan form, is that if you're not over, if you're missing eigenvalues, you can't really do it over that.
Yeah, so why we can say that all the eigenvalues are 0?
Well, because what this shows right here is every root is 0, and any field contains 0. Right, so, all the roots of the characteristic polynomial have 0. Because if you have any eigenvalue, any lambda, then lambda has to be 0. So,
Yeah, but if the characteristic polynomial, for example, in the 2 by 2 are x squared plus 1, what happened there? We don't have eigenvalues.
so yeah, so if, for example, if you have a 2 by 2 matrix over the rational numbers, and you get characteristic polynomial x squared plus 1, it does not have a Jordan canonical form over the rational numbers.
It doesn't correspond with a nilpotent matrix.
Exactly.
I'm just saying, like, that's not the characteristic polynomial of a nilpotent matrix.
For the nilpotent matrix, the characteristic polynomial, if A is an n by n nilpotent matrix, then all eigenvalues are 0. Right? And so characteristic polynomial
My question is, why did that happen?
why does this happen?
Yeah.
Right, because if AX is equal to lambda x and A to the n is the 0 matrix, then start applying this matrix to this polynomial, so you get like A squared x is lambda AX, right?
Yeah.
Which is lambda squared x.
Sorry about that, but my question is, why we know that A has eigenvalues?
Well, because it has to have an eigenvalue over some field, right? Because when you take its characteristic polynomial, you get a polynomial over that field. And that polynomial may or may not have roots over that field, but it's got roots over some field. And we're getting into Galois theory and talk more about that later, right? But I don't care what the matrix looks like.
Oh,
I don't care what the matrix looks like.
okay.
If it's nilpotent, and in fact, if you look, yeah, in fact, I'll pull it up here in a moment. So if you keep going like this, zero. So this gives that any possible eigenvalue is 0. Everybody agree with that?
Right.
And the eigenvalues are the roots of the characteristic polynomial. And of course, the characteristic polynomial matrix or field, it has to have roots somewhere, maybe not in the field that you started with, but you can make the field bigger. And we'll talk about that in Galois theory as well. So if I have a 5 by 5 matrix, if I have a 5 by 5 matrix, then here are my possible invariant factors. And like I pointed out, the invariant factors and the elementary divisors are the same thing in this case, because you've only got one prime, and that prime is x. So it could be x5, right? That's the only way to be one of them. And remember, the product of the invariant factors needs to be the characteristic polynomial. So you have x4 and x cubed and x squared. All right. That's the only way to do it with one. These appear to be the only ways to do it with two. Let's see, I can do three. There. I can do x squared, x. Have those. And I guess that exhausts it for three, doesn't it? I do four. X squared, x. Right, I think that's the only way to do that. Or I could do.
So it looks like the partitions of 5.
That's exactly right. So that was my next point, actually, is that, so what you're basically doing in this particular case is you're counting the partitions of the number five.
And in general, it'd be the number n.
Okay.
Yeah, sure, yeah, so this gets out of hand pretty quickly, right, if I talk about n by n, you know, what the matrices. So one, your Jordan canonical form. That. Number two, you have a four block. Zero. 5, 4, 1. In case three, you have a three block. And then a two block. Like that. In case four. Looks like I've got what, a three and then two ones. In case five, I've got six blocks. And then three blocks. And then seven. All zeros all the time, right? So if you have any 5x5 nilpotent matrix that you can come up with, it may look pretty nasty actually, but you can conjugate it to one of these 7 forms, right? Which is convenient really, because these 7 forms, I mean, let me give you kind of an example of how dramatic this might be. Let's see. So last time I taught this course, which was last year, I gave the following matrix here and asked them to, well, I'll see what I do. So if you look at, just what that's homework. Yes. You know what? Actually. Ultimately saving an enormous amount of time. So if we look at this right here. This matrix right here is nilpotent. Right, I mean, you would want to test that, would you? But actually, for this one, for, number 1B, if you compute the Smith normal form of this, what is it, 7 by 7? 1. One. Let's see. X squared, I see the short one. I mean, X squared. So this really rather terrible looking matrix, notice it's nilpotent, it's only got 1 0 in it. The Jordan canonical form of this, so there's a conjugate of this that looks like, what is it, 2 2s ago? 0 1 0 0 0 1 0 0 0 1 0 0 0 1 0 0. And that's just certainly not obvious. By the way, what's the index of nilpotency of this? Right? What's the smallest power that I have to take, make it 0? It's the third power. That's right. It's the size of the largest invariant factor, which in this case is 3. Yeah, I mean, it's not obvious, right? But if you cube that monster, you will get 0. Let me give you one more kind of groovy application, I guess. Consider all vertical matrices over Z2. So I'm gonna write Z. Let's just look at 2 by 2 matrices over Z2 that are invertible. By the way, how many of these are there?
Right.
I think there's 6. Right? Because think about it this way, and I don't mean like equivalence class. I mean all of them. I will list all of them. So think of it this way.
Oh, yeah.
The top row can be anything except 0 0, right? And 0 0, you're totally hosed, right? So let's pick the top row to be this. The second row can be anything linearly independent. So I could go 0 1, make my identity, or 1 1. The top row could be a different linearly independent vector. And now my bottom row can be anything that's linearly independent of that. And finally, my top row could be 1 1 1. And there they are. This is an exhaustive list of all the invertible 2 by 2 matrices over Z2, right? This is actually a group as well, right? Because when you multiply 2 by 2 invertible matrices over Z2, that's what you get. What is this group isomorphic to? It has to be S3, right? Because it's not cyclic. You kind of tell that. But you can actually show, well, of course, the only group of 4 is 6. It's not big. It's isomorphic to Z2. Oh, and here's a quick proof. in Z2, I'm sorry, in Z6, how many elements are there in order two? Exactly two, one, and only one, right? This element and this element both have order two. End of story, it can't be Z6, right? It's got to be, so the only other group is S3, so that's what it is. All right? Now, let me point out, y'all remember the class equation? Right, basically you can sort of, the group, you can count it at the center, which in this case, in the S3 is just the identity. And then you can look at all the conjugacy classes, right, of every element. This canonical forms will help you find the conjugacy classes, right? So, how many, let's say rational canonical forms are there? And this will determine for me what the conjugacy class is. So notice, let me kind of, this might help us in our quest here. Let's look at what the characteristic polynomials volumes are, right? That'll help me. This one is x minus 1 squared. By the way, sometimes I might write x minus 1 and x, sometimes I might write x plus 1 because it doesn't matter. Plus and minus 1 are the same thing here. Same characteristic polynomial. This is x squared minus 1. Right? And I can also rewrite this as, right, that's because again, characteristic 2. This one's a little wonkier. This is x squared plus x plus 1. This one is x squared plus x plus 1. And this one is x minus 1 squared. Now notice what happens, if you look at these polynomials, it's easy to factor these into primes, right? This is just x minus 1 times x minus 1, x minus 1. This one, what about factoring this polynomial into C2? It's already prime, it's already irreducible, right? So let's look at the rational canonical form we can form. Well, you can have, you can have two rational canonical form blocks. And that's the only way you can do that. And there's your identity, right? So this is one equivalence class. What's another way you can do it? So we've now played off of this. This is when your invariant factors are x minus 1, comma, x minus 1. The other choice you have is if this blob right here is just a single x minus 1, the single invariant factor. And the rational canonical form here, so this polynomial actually turns out to be x squared plus 1 or x squared minus 1, whatever you like. And so I get 0, 1, and 1, 0. So it looks to me like all of these, this one, and this one. Whoops. Sorry. These three are all be conjugate, 3 elements, 4 and 2. Right. And what about this last one? Well, this is the last. Now you have invariant factor x squared plus x plus 1. And if you form the rational canonical form here, only 1, 1. And notice, it just turns out that here's our representative here, but these two are in conjugacy class as well. So what we see here is the matrices tell us that you got the identity. That's the centerpiece of the class equation. And then you have a conjugacy class of all the elements 4 to 2, and a conjugacy class of 2 elements 4 to 3. So there's an application of this to just taking apart some group theory. And you can do this with any group that you can represent with a matrix representation. Everybody okay? Okay. Okay, questions? All right, yes.
Oh, I don't think I understand when you chose to split to have one large factor.
Right. So think of it this way. So let me take this apart from another point. Okay. Suppose I have a 2 by 2 matrix over Z2, all right? Would everybody agree that no matter how I cut this pie, it's going to have a characteristic polynomial degree 2, right? Okay, well, you know what? Let's exhaustively list every polynomial degree 2 that could possibly. Well, it could be x squared. It could be x squared plus 1. It could be x squared plus x. And it could be x squared plus x plus 1. There are only 4 polynomials over Z2. And of course, I can make it monic. Well, if it's not monic, it's not degree 2 here, right? So, now, I did say invertible, right? So only 2 of those polynomials work. Can you tell me which ones? Or which 2 don't work and why do they not work?
X squared plus X don't work because they have 0 is 0.
That is correct. Both of these have eigenvalue 0. No way is it going to be invertible. Agreed? So your only possibility for polynomials that are characteristic polynomial for an invertible 2 by 2 over Z2 come from these polynomials here, right? Now, suppose this is the characteristic polynomial. Well, this one's kind of wonky because that's x plus 1 squared, right? What are the possible invariant factors? Or elementary divisors is all the same. For this irreducible, or for this polynomial. Number 1, it could be x plus 1 squared. Or number 2, it could be x plus 1, x plus 1. Right? Those are the 2 possibilities you can have. Because remember, the product of the invariant factors has to be the characteristic polynomial in this case. So either it stays as a single prime power blob, or it's 2 smaller pieces. Right? This one is the identity. Right? And the other one is the one that gave back. Agreed? Okay, so far. And for the other one, if on the other hand you have characteristic polynomial x squared plus x plus 1, well, this is a quadratic polynomial over Z2. So if it reduces, it has to have roots. It has to reduce into 2 linears, right? And it's easy to check that if you plug in 0, you plug in 1, no root, right? So this polynomial is in fact irreducible, prime. So there's no choice on your invariant factors here. It's just that one block, because that thing's a prime. And so the only choice here is 0, 1, 1, 1. Right, because that blob is your stuck invariant factor. Does that clear up what you were asking? Okay. Other questions? Here's the Galois theory. This is arguably the most fun part of the course here. So let me start off with the definition. This is kind of a strange way to put it, but we've been dealing with lots of rings, modules, so forth. Definition 8.1.1. A field. How many of you early on in your math career, like way back early in undergraduate, read a definition of a field? It was probably long, wasn't it? Because they probably said, okay, for any, they go through all the associative and all the commutative properties of addition, and it's got this huge list, right? And then they go through the multiplication and every non-zero element is particle, blah, blah, blah. And distributive properties. The first time I read a definition of a field, it was basically kind of a setup for linear algebra. It was like a long thing. Then you get a little bit better. A field is, so it's an abelian group under addition, and the non-zero elements form a group under multiplication, and you have the distributive property. Right, now here is, now that we're all graduate students and such, here is when we come to the top of the mountain, the lazy person's definition. A field is a commutative ring with one such that 0 is a maximal ideal. Right, you could define it that way, right? Because what does this mean? This means that any element that's not 0, say A, has to generate the entire thing, which means that A is a unit, right? So it means that anything works. So a field is extremely boring from the point of view that if you like ideal theory, if you like factorization, things like this, very boring, right? That doesn't mean that there's not a lot of cool stuff going on. And in fact, that's the whole point to this, is studying automorphisms of fields and their behavior, and it also allows us to construct really nice examples and rings, et cetera, et cetera. But let me make an observation. So this is kind of a redundant thing that I'm saying here, because I'm saying that, right, what I'm saying is, I assume that there is a identity in the field that's not 0. I'm assuming that about rings as well, unless I tell you otherwise. But I want to key on that for a moment. Any field contains 1. So you have kind of two possibilities here. Number one. In times is not zero for any in the math. We call this case characteristic zero. Y'all are familiar with this, right? So in other words, you can't add one to itself a finite number of times you get zero, right? That's it. What can you say about a field that is of characteristic zero? Yes,
It contains an isomorphic copy of two rationals.
that is correct. Like there's an isomorphic copy of Z inside the field, right? Agreed? But then again, this is a field, which means that every non-zero integer is invertible. So in fact, any field of characteristic zero must contain Q, must contain the rational. So in other words, in characteristic zero, Q is the most economical field possible. It's the smallest possible. Right. The other case is, all right, maybe it's not characteristic. Two, there exists in that numbers such that n times 1f is zero.
But then has to be prime, no.
Well, the minimal positive there has to be
Yeah.
prime.
Right.
Right.
Sorry.
If n is minimal in the natural numbers such that this happens in F, then n is prime. Z is bothers me, so I'm gonna change the notation to P prime now, right? And in this case, ZP is containing an F, where this notation means Z mod P, not P addicts. Sorry, I should apologize to my old number theory teacher for writing it that way. So this is called if F is a field, then its prime subfield is Q if the characteristic of F is zero, and ZP if the characteristic of F is equal. So this is often called, and again, it's sort of the minimal field contained in whatever field you have. So in particular, it's nice to notice that if you have any field with characteristic zero, it's an extension. It contains Q. And if you have any field with characteristic P, then it must contain CP. And those are the only cases for fields. Fields have to have either characteristic prime or zero. Right. So speaking of extensions, we get the following definition. Definition: a field K is an extension field of F. A extension field F. If F is in K. Simple as that. It's just an extension field of K, or of F is a bigger field, K that contains F. Now, let me point out something. K is a big field containing F, right? Notice that if you add two elements of K, you get an element of K, right? In particular case, an abelian group. And you have a scalar multiplication from F. Anything in F times something in K is still in K. So K is a vector space over F. Which is one of the reasons why we look at modules before we look at Galois theory. K is actually a vector space over F, and the dimension of K over F as a vector space is denoted, this kind of notation here, that way. So when you see this, let's look at index thing in group theory. This just means the dimension of K is an F vector space. And additionally, one more thing to this rather sweeping definition. If E is a field with F E K, then E is called an intermediate field. Extension K over F. Sometimes this is written K over F as an extension field, so that's a notation you see sometimes. Okay. So now here it comes. You probably smell this one coming. Theorem. F inside E, inside K of fields. Then by the way, sometimes this is called the degree of the extension. So let this over here. Anybody want to guess this?
Degree of E over F times the degree of K over E.
Exactly. And that's what it is.
But we have that only if the extent the K plus F is finite, right?
No, this is generally true. It's most useful when K over F is finite. So what I'm gonna do is I'm actually gonna do a proof where we're gonna do a cardinality kind of argument. Yeah, but this is true even for infinite. So for example, if this extension is of an uncountable degree, and this one's countable, then that one has to be countable, for example. So proof. Let's let U be this thing right here is going to be a basis for E over F. Okay, and I'm gonna have V a basis for, K over E. And what you might suspect, my strategy here, so I've got,
Maybe you can be expert.
right, so what I wanna do is, I wanna somehow smash this together and make a basis for K over F. U is the basis here, V is the basis here. I'm gonna let X be this set. U, I, V, J, I, and I, J, K. So I'm gonna build this new set here, basically by smashing all pairs together. And I claim that this is a basis for K over. So what do we have to do? We have to establish that this is a linearly independent spanning set, right? So let K be an arbitrary element of K, so I can write this as, let's see. Here's my basis for K over E, so I can write this as E1, V1 plus E2, V2 plus EK, that's probably a fourth choice, EN, VM, right? And on the other hand, each of the EIs are in E, so let me look at, my notation here. Each EI like as the following mess. AI1, or, yeah, on that A, in that AI1, yeah, how many am I use now? Let's see, U1 plus AIN UN. Now, you may criticize me because I'm going to singly index the U's, but that's okay really, because I could just take all the union of all the U's needed for all the EIs, and some of these AIs can be zero, right? And so K is now a linear combination. Oh, and by the way, of course, here AI, J is in, base field F, UI, right? Because you plug each of these in here and multiply it through, and everything's a linear combination. So spanning's not too bad. As far as linear independence goes, right, linear independence is just kind of a sequential thing, right? So if you express, what you do is you express K as a linear combination of the UIs, VIs, group things out and use linear independence separately. See if you can figure that out, and we'll go over that next time. Any questions? Any questions? All right. Oh, yes.
That proof our argument for the infinite cases too?
Yes, because what we're gonna basically, so here's the end game. The end game is, this thing is the cardinality of I, thank you. This thing is the cardinality of J, and this thing is the cardinality of I cross J, which is the cardinality of I. times cardinality J. So that's the end game on that. Okay, other questions? Yes,
Are we introducing any new notion here, or is this just the extension over groups here in that notation? Is that notation, we're referring to the same thing, right? As if K and F were only groups?
no, because this is the dimension is a vector space.
Okay.
K is a vector space over F, which might be a different thing. Like if you have like finite vector spaces, it'll be the same, but
Okay.
yeah. Yeah, let me think. I mean, I wonder if it translates. So,
It's the same as it.
yeah, maybe it is. I mean, so if you have like, if this is a finite dimensional thing, the number of cosets. Yeah, I think it actually is the same, but let me cogitate that. Yeah, I think that's right. Okay, all right, we will see you